Good evening, everyone. My name is Malcolm Butler, and I'm the Dean of Science here at Carleton University. First, on behalf of the Faculty of Science, I'd like to welcome you to this evening to our 2011 Herzberg Lecture. Now, each year, the Faculty of Science hosts the Herzberg Lecture in honor of Dr. Gerhard Herzberg. Dr. Herzberg taught and conducted research at the University of Saskatchewan and University of Chicago before moving to the National Research Council in Ottawa in 1948. He was most widely recognized for his work in atomic and molecular spectroscopy, and in fact in 1971 was awarded the Nobel Prize in Chemistry. Dr. Herzberg's connection to Carleton included serving as Chancellor of the University between 1973 and 1980. But throughout his career, Dr. Herzberg was dedicated to furthering freedom of inquiry in science and was a strong proponent to the important and relevant role of science in society. A lecture series in his name, exploring a science-related topic of general interest, seemed a very fitting tribute. Now, our speaker tonight is Dr. John Cassidy. Dr. Cassidy is a research scientist and head of the Earthquake Seismology section at the Geological Survey of Canada, Natural Resources Canada, based in Sydney, BC, as well as being an adjunct professor at the University of Victoria. Dr. Cassidy specializes in earthquake hazard studies and in Canada and has published numerous articles on this subject. He works closely with the engineering community and with emergency management organizations that utilize the results of earthquakes research. Dr. Cassidy is extremely active in public outreach activities and has served as a member of the Canadian Association of Earthquake Engineers Reconnaissance Team that traveled through the regions of Chile that were hardest hit by the magnitude 8.8 quake in 2010. Dr. Cassidy's international collaborations include working closely with scientists in Chile, Mexico, the US, Japan, Italy, and France, with the ultimate goal of working to minimize the impact of future earthquakes. I think we're very fortunate to have Dr. Cassidy with us tonight, and I'd now like to ask you to please join me in giving him a warm welcome as he presents his lecture, Shaken and Stirred, The Cost of Earthquakes and How Science Can Help.
Thank you very much for this opportunity, and it really is an honor to be here this evening. My very first job as a physics student was at the Herzberg Institute of Astrophysics in Victoria, and science, the application of science for society, is what drew me from physics into the earth sciences, and specifically into earthquake science. So there are some good links here tonight. And what I'll talk about today is exactly this: the cost of earthquakes, the impact of earthquakes on society, and how science can help to minimize the impact, the cost. And so I've broken the seminar up into three sections. The first is dealing with earthquakes in general, what causes them, where do they occur, why, and how. And notice that I've avoided the use of when, because we can't predict earthquakes. So if that was a question, that's the answer. Secondly, reminder of the impacts of earthquakes on society. And then mainly what I'll talk about is the science of earthquakes. What's new, what's happened over the past 5 or 10 or 20 years, and how can we apply those results to reducing losses and impacts of earthquakes. So, the Earth, the surface of the Earth, is like a giant jigsaw puzzle. It's made up of tectonic plates, and these plates are moving relative to one another. They move at about the same speed that your fingernails grow, which is not really fast, but it's somewhere in the range of 5 or 10 centimeters each year. If you didn't trim your fingernails during your lifetime, you would have about 10 meters. And that's what has to happen along these plate boundaries. These plates have to move that much over centuries. So the movements have to occur along these active plate boundaries. Perhaps 2, perhaps 5, perhaps 10 meters in a century. The plates aren't moving every day. They typically are stuck together, storing energy. But when the rocks break and slip, that is the earthquake, and so the earthquakes tend to occur at these plate boundaries. You might think you're safe here in the middle of a plate, but you're not. You may have felt the magnitude 5 earthquake just north of Ottawa last June. So we do see large earthquakes as well occurring in the middle of these tectonic plates, just not quite as frequently, but they do happen in these areas. And the red stars are some of the earthquakes I'll talk about tonight. The Haiti earthquake of 2010, the Chile earthquake, the recent New Zealand events, and Japan, a magnitude 9 earthquake in Japan. Plates can do three things. They can either move towards each other, they can collide, as they do off of the coast of British Columbia. This is a convergent boundary or a subduction zone. Plates can slide past one another, like the San Andreas Fault, or the area of Haiti where the large earthquake occurred. And here plates are simply sliding past one another. Or plates can move apart. And for example, the Mid-Atlantic Ridge, where the Eurasian plate is moving away from the North American plate. These are the three basic types of plate motions, and it's these boundaries again where the earthquakes occur. Here's a map of, this is about 5 years of earthquake activity. And again, it looks like the plate boundary map. So almost all of the earthquakes are defining those plate boundaries, the Mid-Atlantic Ridge, South America, around the Pacific Ring of Fire. About 90% of the world's earthquakes occur right in this zone. But there are also, as you can see, earthquakes in the middle of these tectonic plates. Here in Canada, we have Geological Survey of Canada locates about 4,000 earthquakes each and every year across the country. This map shows you where some of the larger earthquakes have occurred, and we have seen damaging earthquakes, magnitude 6, magnitude 7, from coast to coast to coast. So from the St. Lawrence Valley, the offshore region of Nova Scotia and Newfoundland, through the Arctic, Baffin Island, we've had magnitude 7 earthquakes, through the Northwest Territories and Yukon, and of course down the coast of British Columbia where the active plate boundary is. Off the west coast, we've seen some of the world's largest earthquakes. We've seen a magnitude 8 earthquake right here, and a magnitude 9 earthquake that I'll talk about shortly, just off the south coast of British Columbia. So it is, Canada is a seismically active country. How do earthquakes occur? Plates are moving, and so here we have a fence that is built across a fault. These plates are moving at depth, but the rocks are actually stuck together near the surface, and so what happens as these plates try to move is you have deformation occurring near the surface. You see this sort of a warping. It's just like you're bending a stick. So you're actually storing energy in these rocks as you bend the stick, essentially. But at some point, just like you can only bend a stick so far, at some point, those rocks will break and slip. The more they slip, the bigger the earthquake. The longer the fault is, the bigger the earthquake. And so this represents the earthquake, the slipping movement. For the largest earthquakes, like Japan earlier this year, we're talking about slipping of 20 or 30 meters in a few seconds. For smaller earthquakes, magnitude 7, we're talking perhaps a few meters, a meter of displacement. And so you have this displacement along the fault, and this is what you end up with. Your fence has been displaced, and here's an actual fence along the San Andreas Fault that has been displaced by movement in the 1906 earthquake. That earthquake, San Francisco, magnitude 8, 7.8, about 6 meters of movement in some areas along the fault zone. The earthquake. When the earthquake takes place, you have movement along a fault zone. The earthquake may be at some depth. Earthquakes occur typically from anywhere from the surface to about 600 kilometers depth through the earth. And so what we're interested in is what sort of motion occurred along the fault zone, how far did the plate slip. It doesn't have to be an even distribution. It's not like moving a sheet of paper. what we're finding is that some areas along the fault might slip 5 or 10 meters, other areas might only move 1 meter, and then other areas might move 4 or 5 meters. So it's quite irregular, the movement along the fault. But this is what's generating the waves that come out and cause the damage. Earthquakes under the ocean or underwater can cause tsunamis. So what we're interested in is really understanding what happens at the earthquake source. How did the plates move? How was the energy released? And how did the waves propagate from the earthquake to the cities where people live? And before I go too far into this, I wanted to just mention earthquake magnitude. That if you go from a magnitude 4 to a 5 to a 6 to a 7 to an 8 to a 9, the shaking level goes up very quickly. It goes up by a factor of 10 for every increase in the magnitude. So if you go from a magnitude 5 earthquake, like the one in Ottawa last summer, to a magnitude 6, the shaking is 10 times stronger. In terms of energy release, it's about 32 times more energy for every unit of magnitude. So as we go from a magnitude 5 to a magnitude 7, you're talking about 100 times stronger shaking, 1,000 times more energy. So things go up really quickly with earthquake magnitude. The other thing that changes is the duration of shaking. And for small earthquakes, magnitude 4 or 5, you might feel strong shaking for a few seconds, for 2 or 3 or 5 seconds. In the event of a magnitude 9 earthquake, like the one in Japan this year, you're talking about several minutes of strong shaking. And in Chile, after the magnitude 8.8 earthquake, talking with people who were hiding under their desk and holding on for 3 minutes during strong shaking. And they described that as being forever, because the power was out, everything had fallen over in their apartment, there were no communications, no cell phones, no telephones, and they were just in the dark, under their table, for 3 minutes of strong shaking, and it was terrifying. So these very large earthquakes produce shaking that continues for a very long time period. Okay, some reminders of recent earthquakes around the world, and you've probably seen a lot of this, but I'll go through a few examples of the impacts of earthquakes on society. And one of the events that I'll talk about is the magnitude 7 Haiti earthquake that occurred right here in January of 2010. This is the boundary between the Caribbean plate, the North American plate. They're moving at about 2 centimeters per year. It's not very fast. It's one of the slower systems, and so consequently earthquakes in this area are relatively rare, typically centuries apart for the very large earthquakes in that immediate area. This map shows the area of strong shaking during the Haiti earthquake, which is this red zone. This was a very shallow earthquake. It's close to the surface and very close to a large city, to Port-au-Prince, right here. And what you can see is the strong shaking extended over an area of about 50 kilometers, but caused a huge amount of devastation. And there were about 316,000 people were killed in this earthquake. Similar number injured. 1.3 million people were displaced from their homes, and 300,000 homes damaged or destroyed. So this was a huge earthquake. And a typical scene after that event in Port-au-Prince. And this damage, the collapse of structures through the city, is largely attributed to a lack of building codes, a lack of preparedness. People weren't expecting this earthquake. They didn't really know what to do when the shaking started. And of course, poverty, because the quality of the construction and the types of buildings were very susceptible buildings to shaking. And being a very shallow earthquake, there were also a lot of aftershocks. This is a plot of some of those aftershocks over essentially the area of strong shaking. So where buildings have been weakened, those buildings that might not have collapsed are now being exposed to additional shaking, and we're seeing more collapses from aftershocks. So aftershocks are a big deal after earthquakes, or something to be aware of and to be concerned about after a major earthquake. Chile. This now is a magnitude 8.8 earthquake. So in terms of energy release, this earthquake is 500 times larger than the Haiti earthquake. It produced a devastating tsunami, produced strong shaking for several minutes, and 523 people were killed during this event. Most of those by the tsunami and not by the ground shaking. So this is a very different scenario than Haiti, and I'll come back to this in just a minute. This was a subduction earthquake. It's where the plates are colliding along the Chilean coast, the Nazca Plate being pushed beneath South America. And here, one of the big differences between Haiti and Chile, an 8.8 earthquake, this is now the region of strong shaking. This is the most populated region of Chile. This is where a lot of the economy is based, right in this area. This is a region 500 kilometers long, about 100 kilometers inland, and there was very strong shaking throughout the entire area. There were damaged buildings and infrastructure throughout this entire region. It was a huge area that was impacted by this earthquake. This map of South America, this is again the area of strong shaking along the Chilean coast, but people in Brazil, Argentina, all across the southern half of that continent felt this earthquake. People in high rises in Brazil felt swaying from this earthquake. So people 3,500 kilometers away from the earthquake felt swaying. So let's bring the Chilean earthquake to Canada and see what we have. And here, for example, this is this area of strong shaking from Chile. If you put that on eastern Canada, it extends from Montreal through Ottawa, Kingston, Oshawa, Peterborough, Toronto, Hamilton, Niagara Falls, Buffalo. Every single one of these communities would experience very strong shaking. That's what happened in Chile. And if we take that earthquake and put it, of course, a magnitude 9 earthquake isn't going to happen here, but if we put it on the West Coast where it has happened in the past, and take that 3,500 kilometer distance and plot it, people in Toronto in high-rise buildings will feel swaying from a West Coast earthquake. And that's just taking the observations from Chile and bringing them to North America. So people in high-rise buildings at these very large distances will feel swaying. And then, of course, this will be called the Great Toronto Earthquake because it was felt in Toronto. But so these are enormous events. They're huge. And I'll just go through some of the impacts in Chile because I traveled through this area immediately afterwards. And in this type of an earthquake, the movements are huge. So the city of Concepcion, right here, moved 3 meters towards the ocean in about 45 seconds. So the entire city moved to the west at the time of this earthquake. A brand new building, this is one of the very few building collapses during this earthquake, rolled over. And it rolled over in the direction that if you pulled out a rug from under someone because of this 3-meter slip. And so this is an area of active research. What role does this displacement, not only the shaking, but the actual displacement, what role does that play in building damage? Relatively few people were killed in this earthquake, 523, but it's still about 12,000 people were injured, 800,000 people displaced from their homes. 4,013 schools were damaged or destroyed, and 79 hospitals were damaged, many of those very seriously. And so, again, over a huge area. So the impact of this earthquake in Chile is enormous, and it will take decades to recover from this type of an event. $40 billion is the estimate, the impact of that earthquake. As we traveled through Chile, this is what we saw over and over again, over that huge area. People who had lost their homes, lost their cars, lost their business. It's not like a hurricane where you have some warning This just happened, and people lost everything in the blink of an eye. Hospitals in the hardest hit area. This is what we saw over and over again. Hospital, this was the emergency room at the Kuriko Hospital. When you need it the most, it's not there. These hospitals were closed. This one was close to collapse. There were major cracks and serious damage throughout this hospital in Talca. So again, over this huge area, we saw over and over hospitals that looked like this. They were closed. People were transferred to temporary facilities. They were in tents. They were, so this was a very, and still is, a very challenging situation. Schools, and we saw, of those 4,013 schools, we saw many. And here's the library. Librarians really hate earthquakes because every school looks like this. But there were many that were seriously damaged, many that will have to be rebuilt. This school in the tsunami zone was nearly destroyed by the tsunami. So the ocean is just on the other side of this school, and you can see the waves came through the wall and then out the other side. We could see the water level about 3 meters in that building. And infrastructure and transportation was challenging. Highways looked like this. This was the main north-south freeway in Chile, and the southbound lanes were closed because this old bridge collapsed during the earthquake. So it was very difficult to move around for a while. And the tsunami zone was complete devastation. That's probably the only way to describe it. Right on the coast, this is what we saw in every community along that coastline for about 500 kilometers. This is what it looked like. There was simply nothing left. Fishing boats that were carried inland, and the amazing thing here is that although all of this destruction that we saw, very few people died because they knew what to do. They knew that when the shaking started, that they had a few minutes to go to high ground. And high ground was relatively close, and almost everyone made it to the high ground. So earthquake awareness and earthquake is critical. Knowing that you live in an earthquake zone is the first step, and knowing what to expect and being prepared and having a plan really makes a difference. And it really worked in Chile. Some of the success stories that we saw in the country. This is a school. There was another school right across the street that almost collapsed. This school, you can see, is designed for earthquakes. It had these big steel beams, this cross bracing, huge nuts and bolts, and it survived perfectly. It was still being used. It was just the beginning of the school year, and people were using this school, so it was perfect. This building was designed to withstand earthquakes, and it was surrounded again by debris, by collapsed buildings. But here was a building that was designed properly and constructed properly, and it survived the shaking. So one of the key lessons is how important building codes are. And we've seen this in previous earthquakes in Japan, but Chile really brought this message home, comparing the Haiti earthquake and the Chile earthquake. Looking at high-rise buildings, those that are relatively modern, those that were designed to modern building codes since 1985. There are about 12,000 buildings in Chile. Of those 12,000, 4 collapsed. And of those 12,000, there were about 50 to 150 that were seriously damaged. So the number is less than 1%, 0.5% to 1.5%. It's a really small number. Building codes really made a difference in Chile. And again, just emphasizing the difference in earthquake magnitude. Haiti, magnitude 7 is 1 square. Chile, 500 times larger. This is the amount of energy released. But the number of people, the number of deaths is, there's a huge contrast here. Building codes, preparedness really makes a difference. And this was, again, the tsunami zone, and these little tsunami warning signs work really well. It reminds people what to do when you feel shaking. People made it to high ground. More recently, in Christchurch, New Zealand, a magnitude 6.1 earthquake, which is not a huge earthquake. It's about 10 times larger than the earthquake north of Ottawa last summer. 6.1 earthquake. 8 seconds of very, very strong shaking. This earthquake was essentially beneath downtown Christchurch. It was within 5 kilometers of Christchurch. A very shallow earthquake. It's caused about $20 billion in damage, the economic impact of this earthquake. 182 people were killed. The population of Christchurch is very similar to Victoria, where I live. Same size of city, the same age, the same building types, similar building codes in New Zealand. But still, the impact of that earthquake is enormous. There were 100,000 buildings either damaged or destroyed in the city of Christchurch and adjacent areas. This is what it looks like today as they tear down damaged buildings. 400,000 tons of silt in the city has to be dealt with after this earthquake. And even today, many months after the most recent earthquake in Christchurch, there are still 40 city blocks in downtown Christchurch that are cordoned off. So if you can imagine downtown Ottawa, if you had to shut down 40 city blocks, the impact on your life and the impact on the city, it's huge. Residents are leaving Christchurch. More than 1,000 people, 1,000 workers per month are leaving the city. The economy has been shrinking. It's estimated about 7% that it's shrunk since February. And to recover from this earthquake, they would have to build a new commercial building in Christchurch every 3 days for the next 10 years to recover what's been lost. So these earthquakes are huge. Even a 6.1, which is not a huge earthquake, the impacts are enormous. The cost of earthquakes, as we've seen from some recent events, Kobe, Japan, about $130 billion. Relatively small and deep earthquake beneath Seattle, about $3.5 billion. Chile, $40 billion, $20 billion, and the most recent, Japan, $200 or $300 billion, and a global impact. These events are huge, and the goal of earthquake science, earthquake monitoring, earthquake science, earthquake engineering is to minimize the impact of those future earthquakes. It's to really understand how the ground will shake and how can we design our structures better to withstand that shaking. And the goal is to save lives and to save money from future earthquakes. So, earthquake science, now the third part of this presentation, and things have really changed over the past 10, 20 years. We have new data. And an example, this is a seafloor image off of Haida Gwaii, off the Queen Charlotte Islands on Canada's west coast. We could never have done this 20 years ago. We could never have seen this level of detail on the seafloor. We see underwater volcanoes. We see the Queen Charlotte Fault running through here. You can image the seafloor with amazing detail, and you can find faults that have been active and get a better assessment of earthquake hazard. So we have new types of data. We have higher resolution data. We have real-time data. We have information flowing in real time. So we have immediate access to ground shaking in the Arctic, in Eastern Canada. Anywhere in Canada, we can see how the ground is shaking as it's shaking. So this provides new opportunities for us as well, this real-time aspect. We have better computers and faster programs, better ways of modeling the data. More accurate models are being developed. So it really is, the past 5 or 10 or 20 years has been really exciting for earthquake science. And for the graduate students out there, we have a lot of data and things are changing still very quickly. So there's a lot that we can do now that is new and very beneficial. And just a reminder that earthquake science, unlike physics or chemistry or biology, earthquake science is a very young science. Data for just over 100 years. So recordings of earthquakes, the old instruments were huge, and the seismograms that were produced, the recordings of the earthquakes, looked something like this. So it's useful, but it's not really useful. It's not terribly useful. This is what you had to work with. 20 years ago, when I joined the Geological Survey of Canada, we were just switching to digital data at the time. So many of the instruments were analog. They were paper recordings that looked like this. There's a little needle up here going back and forth. And this is what a big earthquake looked like on a paper recording. So here's a magnitude 6.8 earthquake off of the British Columbia coast in 1992. This is the recording, and it's not really useful. It's sort of useful, but it's not really useful. It's clipped, it's too faint. You don't really see a lot of detailed information in that waveform. But digital data, this is the same earthquake recorded on a broadband digital seismometer. Now, you can see all of the details of this earthquake. You can see how it began. You can see the middle part of the shaking. You can see the big surface waves coming through. So there are details here that we could only dream of before digital data were available. And with these new data, the digital data, you can now start getting images of the earthquake. You can identify where the plate slipped, how much the plate slipped, where energy was released and where energy wasn't released. So you can start getting very detailed images of these earthquakes. And this information feeds directly into our building codes, into bridge codes and dam codes. And this is the primary means of protection against earthquakes, is through these codes and standards that are developed. Starting in 1953, and these are updated frequently as new information becomes available. 1970, there was a major improvement in the earthquake hazard models. 1985, 2005, most recently 2010. And as we speak, Dr. John Adams is busy working on 2015 codes. So these are being updated and improved on a regular basis, incorporating the latest information. So the idea of where we want to go, we want to improve the building codes. We want better hazard maps. We want more detailed maps. This is a map of California, the San Francisco Bay Area. And here you can actually identify the probability of a major earthquake along these various faults in the next 30 years. So you're not predicting an earthquake, but you're saying this section of the fault is most likely or more likely to experience an earthquake than down here or over here. So you're getting better information on where do you want to focus your efforts for earthquake preparedness mitigation. But some of the things that we're working on, time varying hazard. How does hazard vary over time? Is the earthquake hazard higher in this region now than it was compared to last month or 2 months ago? Better spatial resolution, better detailed maps. Going back in time, extending our record of earthquakes. More than 100 years, we need sometimes 1,000 years or more than 1,000 years. So going back in time. And developing detailed maps for cities like Ottawa or Vancouver or Montreal. So, and mostly we're learning from recent events around the world, like Chile and Japan and New Zealand. As new data come in and we have new analysis techniques, learning from those events and applying that to our earthquake hazard models. One of the things that we can do now that we couldn't 20 years ago is getting these very detailed images of how the fault slipped during an earthquake. This was the Chile earthquake in 2010. The movement here was about 10 or 15 meters, 15 meters. Areas of low slip, only a few meters of movement. So we can actually map out in incredible detail how the rocks moved during this earthquake. And so what this allows you to do is to identify where aftershocks are more likely to occur, because eventually all of these areas have to be red like that. So large aftershocks have to occur here, or future earthquakes have to occur here So eventually, this entire region needs to fill up with slip. So these types of images that we can now produce give us a better idea of where future earthquakes are more likely. We use GPS data to measure the surface of the Earth. How is the surface moving? Where is energy being stored? Where is deformation taking place? This is what one of the antennae looked like on Vancouver Island, using satellites to get very precise locations between two of these sites. And here we're looking at a site in the interior of British Columbia compared to a coastal site. And what we see day in and day out is that Vancouver Island, parts of Vancouver Island, are rising, and Vancouver Island is moving towards Vancouver. So we see this compression taking place. Every day we can measure that. It's exactly what was happening in Chile before the major earthquake. It's exactly what was happening in Japan before the earthquake this year. So the computer models that we developed, this is a simplified version. My colleagues who've been working on this find this buckling. So what's happening is the Juan de Fuca plate offshore is moving towards North America. It's moving at about 4 centimeters per year here. It's moving down here. But where that plate meets North America, these plates are locked together. They're actually stuck together and bending. It causes this warping, which happens to be right where Vancouver Island is, right where I live. So Vancouver Island is rising, moving towards the mainland. This has been going on for 311 years, but eventually everything will reverse, and areas like Victoria that were moving towards the mainland will suddenly move towards the ocean. Tsunami will be generated offshore. This plate will slip 20 or 30 meters. So it's GPS data that have allowed us to develop these models and are now feeding into our earthquake hazard maps and into our building codes. So in Western Canada, for example, these GPS measurements that show us how things are moving, where energy is being stored for future earthquakes, we see along Vancouver Island, this region moving towards the mainland, a lot of compression going on here. Along Haida Gwaii, the Queen Charlotte Islands, we see the movement to the north. And one of the new results is that actually extends inland. So along the coast mountains, we're seeing some substantial movements, which would suggest, even though we don't see or haven't seen large earthquakes in that area, that there's the potential for events extending inland from the plate boundary. And then up in the Yukon and Northwest Territories, we can see this movement inland. And by the time you get into the interior of British Columbia, there's essentially no motion. So it's very stable, which makes sense. We don't see very many earthquakes through the interior of British Columbia. Most of the earthquakes are out here where that active deformation is taking place. But these GPS data are new, and they help us to identify areas where earthquakes are more likely to occur. So better earthquake hazard maps and better volcanic hazard maps. We have some new instruments on the seafloor off of Vancouver Island. There's a large fiber optic cable on the ocean floor with power, with internet. You can dial up and see data in real time from any of these sites offshore. This extends from the ocean ridge, where a new ocean plate is being created, where the Juan de Fuca plate is being created, right through to where that ocean plate is subducting or being pushed beneath North America. So we have instruments here monitoring tsunamis, monitoring earthquakes, counting fish, doing all sorts of things. So it's used for many purposes, but earthquakes and tsunamis are a few of those. This is what they look like when they were being deployed by these little underwater robots. So the seismometer is inside this case, being put beneath the ocean and then covered over so you actually don't know it's there, except for this cable and a few fish going by. So these instruments, again, these are very new. These are only about a year or 2 years old. And they're allowing us to start looking at the area where we know those magnitude 9 earthquakes are going to originate. So we can start looking for small earthquakes in the area, monitoring earthquakes in that region where the plates are locked. It's the first time we can do that. We can map the structure of the ocean plate, how thick is it, how large can the earthquakes be in that ocean plate. We have real-time data, so you can dial up and see some of these data coming in, which provides some new opportunities for warning systems that I'll talk about in just a few minutes, both for earthquakes and for tsunamis. So we can, as I've shown you, we can map out when an earthquake occurs, how much the rocks have moved along a fault zone. This was a recent earthquake just south of California. It was in Baja, in Mexico. So you can actually say along this fault zone, the plate slipped 4 meters, 1 meter, and you can use a computer model to generate changes in the stress field. So these red zones are areas that the stress has increased. These rocks are under more stress than they were before the earthquake. The blue zone stress has been released, which is a good thing. So you have a couple of red zones and a big blue zone. This also is relatively new. What we can do is areas where the stress has increased are those areas where aftershocks are more likely to occur. So you can actually see here for Haiti, for example, that most of the aftershocks are in the red zones. So this gives you a new tool to understand where aftershocks are more likely. In Southern California, this was a sequence of large earthquakes, magnitude 6.5 to 7.2, and the first one occurred down here. There was a red zone with a lot of aftershocks, but then there was actually a larger earthquake that occurred in the red zone up here. So this earthquake, the Landers earthquake, generated its own red zones, which then triggered another earthquake over here, a magnitude 6.5. So there was a sequence of 3 large earthquakes that fit with this stress, increased stress following slip along a fault zone. And in Turkey, the North Anatolian fault system, which is like the San Andreas system in California, plates sliding past one another. So the North Anatolian fault here from east to west, and what we've seen over the past 60 years is a sequence of earthquakes marching along towards Istanbul. So here we see in 1939, this big red zone. This was an earthquake, about a magnitude 7.8 earthquake that occurred along this section of the fault. A few years later, in 1942, and then 43, 44, 57, 67, and then in the Izmit earthquake, I've forgotten the year, but what we see is this progression of earthquakes, of large earthquakes, along this fault zone, attributed to the stress. So it's a way of not predicting earthquakes, because you're not saying exactly when an earthquake is going to happen, but it gives you an idea that the areas over here are much more likely to experience a strong earthquake in the coming decades compared to an area down here or over here. So this also is a new tool that is useful for earthquake preparedness. And this is being used. In Istanbul, there are a lot of measures in place right now because they understand that this sequence of earthquakes has been coming towards that city over the past 60 years. So mapping changes in the crustal stress field allows us to identify areas more likely to experience aftershocks and areas that are more likely to experience earthquakes in the coming decades. Often we need to go back in time. We need to understand the earthquake history of a region for nuclear power plants, for example. So paleoseismology is a really important part of our science that has been evolving over the past few decades. This is some work of John Adams off the coast of Vancouver Island, and what was discovered in these deep sea cores in the mud is that every now and then you see a layer which is material that came from onshore. And it was a submarine landslide that was brought down the continental slope, and you see a whole sequence of them here. These occur all along the coastal regions of Cascadia, the region from British Columbia to California. and this now correlates with onshore recordings with paleoseismology. The history of earthquakes going back thousands of years. So this particular record showed us that these events were occurring on average 500 to 600 years apart, but there's a very large variation. Sometimes it's 200 or 300 years, other times it's 700 or 800 years, so there's significant variation. But it was a clear indicator that these large earthquakes occur and have occurred going back in time, thousands of years. Another way that we can get at earthquake hazard that we couldn't do 10 or 20 years ago is the detailed mapping of cities, of urban areas. How does the shaking vary across a city? And this is some work of Dr. Morazidian here at Carleton University and my colleagues at the Geological Survey of Canada, working together to produce this very detailed map for Ottawa. What are the soil conditions and what might you expect in future earthquakes? The earthquake last summer, the 2010 earthquake that you might have felt, these are recordings of that earthquake at a number of sites across Ottawa. And you can see here on the rock sites, there's some shaking going on. And as we move down to firm soil, this is a soil, but it's a dense soil, there's a little bit stronger shaking maybe. And then when you get onto very soft soil, you see significant shaking and much longer duration shaking. So here, 20 seconds of shaking compared. So compare this recording on soft soil with this one on rock. It's quite different. So these types of detailed maps are now being developed in urban areas here and around the world. And these allow you to identify areas that are more likely to experience strong shaking in the future. They allow you to provide obviously more detailed maps and better planning, better land use planning. And finally, another new application, something that's being just developed and is just starting to be tested, and that is earthquake early warning. And this is not earthquake prediction, this is early warning. And this is what an earthquake looks like. Here's a P wave, you'd feel an up and down shaking. Here is the S wave, and you would feel side to side shaking. This is the wave that typically causes damage, this horizontal shaking. These S waves travel at about 3 kilometers each second. So the farther away the earthquake is, the longer it takes the waves to travel. So if you ski at Whistler and you know how far Whistler is from Vancouver, it's about a 90-minute drive. It takes the P waves about 18 seconds. If an earthquake happened in Whistler, it would take the P waves, these guys, 18 seconds to travel from Whistler to Vancouver. The shear wave takes about 32 seconds. So if you happen to be on the phone with somebody in Whistler and they say, there's a big earthquake here, before the phone goes dead, you have about 30 seconds before the strong shaking hits. So that's the warning time. And similar numbers for Montreal. If there were a big earthquake near Montreal, it would take about 25 or 30 seconds for those waves to travel to Ottawa. So there's a time window where you can be warned that strong shaking is coming your way. And just some examples. So here's Vancouver. If there were an earthquake just across the strait on Vancouver Island, and you had enough instruments in the area, and you could say, yes, a major earthquake has happened, you automatically locate it, automatically calculate the magnitude, and say, yes, this is a damaging earthquake. You can send the information to Vancouver, and you would have about 20 seconds at most before the shear waves arrive. If the earthquake is offshore, where most of our big earthquakes are, then you might have anywhere between 60 seconds and 90 seconds of warning. So now it's becoming a little better. And if it's one of these giant subduction earthquakes, like the one off of Japan earlier this year, so the subduction zone extends from right here down to California, and if that earthquake started in California, and started rupturing up the coast, you could have as much as 4 or 5 minutes of warning in Vancouver before the strong shaking hits. So it's not a lot of time, but there is some time. And what you can do you need automated systems. You need to automatically locate the event and calculate the magnitude, push out the information, receive the information. But what you can do is, and what's happened in Japan, for example, you can stop trains. That happened in Japan. The high-speed trains were stopped at the time of the earthquake, when the earthquake system alarm went off. So you can stop trains, you can stop traffic from going onto bridges or into tunnels. You can close valves or switches at critical facilities. Nuclear power plants in Japan were shut down automatically before the strong shaking hit. In hospitals, there might be a bell that goes off, and surgeons can put down their scalpels before this strong shaking hits. Because it really is strong shaking. I mean, the shaking is back and forth. It's very strong shaking. So you can do some things here with relatively short time windows. And in Japan, there are some really good videos of how their system that's being tested, how it worked. And it worked very well. What didn't work well in Japan was the tsunami and the understanding of the tsunami hazard in those coastal areas. But the earthquake warning system that they're testing worked very well. So all of these new methods that we have, the new data sets, these really allow us to improve our earthquake hazard models. And what we can do now with a better model is to focus our efforts on high-risk areas. There's no point in spending a lot of time designing a building in northern Manitoba when the hazard is here and here and here. So it allows us to focus our efforts in regions where we need to focus our efforts. And this is happening. We're making, I think, a lot of progress. This is in Victoria, for example, Vancouver Island, retrofitting bridges, making them stronger. These giant shock absorbers have been added to this bridge where I live, not far from where I live. Schools are being updated to withstand shaking, adding a light roof, adding strengthening through these brick buildings. Old brick buildings are being updated and retrofit. You can see the steel beams here. It doesn't look pretty, but it works. And education is really important. When I was a student in elementary school, there were no earthquake drills. Now this is a part of school life. So several times each year, there are earthquake drills that are being held. So students know what to do when the shaking hits. And this is really important. So just to summarize, I hope, I probably don't have to remind you of the impacts of these giant earthquakes on society, and not necessarily giant earthquakes, but magnitude 6, 7, 8, or 9. Huge impact on society, a huge cost. And the advances that we've been making in science and also in engineering, I haven't talked about any of that, that's an engineering story, but there have been huge advances in earthquake engineering, and the integration between the science and the engineering that has taken place is really making a difference. And we see that. We've seen that in recent earthquakes. We've seen it in Japan. We've seen it in Chile. The difference that the science makes, the applications of the science to saving lives and to saving money and reducing the impact of earthquakes on society. But again, for the grad students and the students in the audience, we still have a lot more to do. So I encourage you to think about how we can move things forward in the coming years. And there's a lot of information out there. Earthquakes Canada website for Canadian earthquakes. Get prepared for preparedness information. The hazard map for Ottawa that I showed is here on the Carleton website, carleton.ca. There's a lot of information that's available. And I thank you very much for your attention.
Hello. So I got a question for you. Do you think that the the fact that Vancouver has been built on a delta is going to complicate matters in terms of a possible future earthquake?
Much of Vancouver, you're right, is built on a delta, and where the Vancouver airport is, and some critical ports, and that land wasn't there 10,000 years ago. It's been deposited over the past 5, 10, 11,000 years. It's something certainly to be aware of, and there are a number of things that go on. There's shaking, there's liquefaction, but knowing about this, you can compensate, for example, for liquefaction. If you know which areas are susceptible to liquefaction, you can put in piles, you can remove the liquefiable soil, so you can deal with that issue, and that has been dealt with in many cases. People in Vancouver, my engineering colleagues at UBC, have been aware of liquefaction for the past 20 or 30 years, and so new buildings and infrastructure built on the delta were built with that in mind, and so much of the infrastructure is very new, and in fact should do very well during an earthquake. And similarly for the buildings, most of the new buildings on the delta are new. They're modern buildings, constructed over the past 20 years to modern building codes. So I would expect them to do very well. We are still learning about how the shaking varies across the region, and that's an ongoing project. But I would, because of the new infrastructure overall, I would expect things to do quite well. Earthquakes have occurred along this coast for thousands of years, and Richmond is still there. It didn't disappear during the last earthquake that we know happened 311 years ago. So, yeah, it's something to be aware of, and you need to mitigate that, whether it's liquefaction or shaking. So that's really the importance of the science, the importance of going back and looking for evidence of previous earthquakes. Was there liquefaction here thousands of years ago? And people have looked on the delta for areas that liquefied during previous earthquakes. There are some areas, but they tend to be pockets. It's not, large, widespread areas. And so people are aware of which areas are most hazardous and which areas are not as much of a concern.
Thank you.
Is Ottawa on a major fault line? And if it is, what does that mean for us? And what does GPS stand for again?
Global Positioning Satellites. It's,
Global Positioning Satellite?
Right, helps you when you're driving your car around. Is Ottawa on a major fault line? Ottawa is in the Ottawa Valley, the western Quebec seismic zone. There are a number of old faults running through this area and through the St. Lawrence. There are old faults running through this region, as there are in most areas of Canada. You can find old faults. The question is whether those faults are active or not. And so identifying active faults is an active area of research, using new methods of trying to image the faults and get better earthquake locations. This is an old fault zones that run through Ottawa and the St. Lawrence. And
what does that mean?
They were active billions of years ago, hundreds of millions of years ago, not necessarily active today.
Do we have any upper limit to the magnitude of earthquakes? And I'm thinking either theoretically or historically. Is there a strongest earthquake that can occur?
The largest earthquake that we've seen, which doesn't answer your question, is 9.5 off the coast of Chile in 1960. And what controls the size of an earthquake is essentially the length of the fault, the width of the fault, and how much the rocks slip, if they move 10 meters or 30 meters or 40 meters. So, there is sort of the longest fault that we know of is actually that fault in Chile. And so it would suggest that the largest earthquake that we might expect is about a 9.5. There are always surprises. We might see one a little bit larger, but we're not going to see a 10 or a 10.5. That would take a fault that goes around the Earth, which doesn't exist.
So my question is, again, thank you for your time. Why are so many highly populated areas located on seismically active or earthquake zones? Like in California or in Turkey or in Japan, all that.
Yeah, many of those earthquake zones are nice places because of the mountains, and it's the tectonics, the movement of the plates that creates the mountains. And so many of those places are just nice places to live. Many of them are flat-lying areas, deltas where they're exposed to tsunamis, areas that are more likely to be experiencing perhaps stronger shaking during an earthquake, or landslides, or tsunamis.
Still very dangerous, though. It's just
They're beautiful places, but a little more dangerous than Flin Flon, perhaps, or there's nobody from Flin Flon here.
You mentioned building codes. I was wondering, what are some of the details that are in them for earthquake proofness, and how much extra does it cost to live safely in an earthquake area?
How much more does it cost to live in an earthquake area? And building codes. The building codes are really for large and engineered structures, so typically 4 stories or higher. Homes, there have been improvements over the years, one of them being securing the house to foundation, which makes a huge difference. So older homes in Victoria, for example, pre-1940s, often are just sitting on the foundation. They're not bolted down. And so that's changed in the codes over the years and is a very good improvement. So bolting down your home, an older home, is an easy thing to do and will make a big difference. The cost of living in an earthquake zone, earthquake insurance is getting more and more expensive because these earthquakes around the world are impacting insurance companies in a huge way, impacting governments in a huge way. And so it is becoming more expensive for insurance. And in Chile and Japan and New Zealand, the governments that are trying to pay for these disasters now, it's not just people who live in the earthquake zone, but it's everyone in the country who pays the price of these earthquakes. So,
but if you're, for example, if you're building an apartment building or something, would it be like 10% more expensive?
It's, my engineering colleagues know the answer to this. I don't, but I was told that it's sort of the cost of carpeting for a building to make it earthquake resistant. It's not a huge cost.
Do you know of any further technological advancements that we can expect to see in the field in the near future?
That's a good question. I think the real-time aspects haven't been fully utilized yet, and that's really just beginning, both for tsunamis and for earthquakes. And combining a number of methods, so combining the GPS with the seismic, combining LiDAR images, very detailed images of faults that can tell us about what happened, where faults may have been active over the past few thousand years. So, but that's a good, I'll toss that out to everybody else. But I think the real-time aspect, where are we going? Where are we going from here? Where are some of the big advances? I think the real-time is really interesting.
Thanks, John, for a wonderful talk. I'm interested in Christchurch. I think in one of your slides you mentioned there was an issue about silt, and I assume this has something to do with liquefaction.
Yes.
How much of the damage of the homes, and maybe not necessarily the businesses or the high rises or whatever their buildings were damaged, how much damage to the homes was based on the fact that silt actually came through the basement structures?
I don't know the number, but I suspect it's a very large percentage of the homes that were damaged from liquefaction, from silt, and there are these photos that just show silt everywhere. It's just bubbled up through the earth, and cars have sunk into this over quite a large area of the suburbs of Christchurch. In the downtown area, it's the old unreinforced masonry buildings that were seriously damaged, almost every one of them.
Well, firstly, I would like to thank you for that really wonderfully presented talk. I think it was eye-opening for all of us who are earth sciences and not in the earth sciences. A lot of really interesting numbers and figures were presented. And I would just like to also thank the audience for being so attentive and asking a lot of really good questions. And yeah, thanks again.
Thank you.
Thank you very much, Claire and Danielle. Dr. Cassidy, we'd like to present you with a small memento of your time here for this presentation. This is a plaque of the poster for your talk, which you signed yourself, so cover your own signature. But something just to take away to remember your time here and to remember our gratitude to you for presenting this talk.
Thank you very much.